The year is 2036, a flood of space rocks, each one carrying enough energy to wipe out a city, is streaking across the night sky. They didn't come out of nowhere. We created them. Decades earlier, NASA celebrated a historic victory. For the first time in history, humanity deflected an asteroid. The DART project, a brilliant planetary defense test, crashed into the asteroid Dimorphos in September 2022, shortening its orbit by 32 minutes. Headlines screamed success. Scientists cheered. But while the cameras moved on to other news, something silent and invisible began to unfold. 37 giant rocks thrown out by the collision are now wandering through the solar system with 3 times more energy than expected. Some of them might hit Mars in 6,000 years, threatening future colonies. Others might come back to Earth in just 30 years. How did we get here? When did humanity's biggest defense experiment turn into a silent threat? To understand what went wrong, we have to go back to the beginning. For millions of years, asteroids have sailed through space in relative silence, orbiting the sun without a care for the worlds below. Earth has always been under threat. About 65 million years ago, an asteroid wiped out the dinosaurs. But until recently, humanity watched the cosmos with empty hands, unable to respond to a real threat. NASA uncovered that painful vulnerability. Despite decades of sky surveys, less than half of the asteroids larger than 140 meters, big enough to cause regional destruction, had been identified. Thousands of them were still hidden, waiting in unknown orbits. The gap was brutal. We had telescopes to watch space, but no proven tool to change our fate if something came our way. Then the DART project emerged, a bold answer to human fragility. The mission was simple: prove that we could redirect an asteroid using the kinetic impactor technique, basically slamming a spacecraft into a space rock at more than 22,000 kilometers per hour. The chosen target was Dimorphos, a small 160-meter moon orbiting the larger asteroid Didymos. Neither of them posed any real danger to Earth. It was the perfect test. On November 24, 2021, DART was launched. The mission carried the hope that humanity would finally have a weapon against cosmic chaos. The first imbalance had been set. We were ready to interfere with the natural order of the universe. 10 months later, on September 26, 2022, DART hit Dimorphos exactly at 7:14 p.m. Eastern Time. The collision happened 11 million kilometers from Earth. The last images sent by the Draco camera showed the moon's rocky surface rushing closer in terrifying detail just before impact. Then, silence. Observatories around the world waited. The Hubble and James Webb space telescopes captured trails of debris spreading through space. The Italian mission Licaia Cube, a small satellite that followed DART, photographed the ejecta cloud, the material ripped from the asteroid by the collision. Within 2 weeks, the scientific community confirmed Dimorphos's orbit had been changed by 32 minutes. The success was overwhelming, beating the minimum goal of 73 seconds by far. But right there, in those first days of celebration, the first strange signs appeared. Lycae. Cube's images revealed something unexpected. Dozens of large rocks, each between 20 centimeters and 3.5 meters in radius, were moving away from Dimorphos at high speed, up to 116 kilometers per hour. It wasn't just dust. They were solid boulders, 37 of them in total, some reaching up to 6 meters across. Scientists quickly realized something was off in the models. The energy and momentum transferred to those fragments were much greater than predicted. The team suspected that DART's solar panels had hit 2 large rocks on Dimorphos's surface, called Atabake and Bodran, milliseconds before the main impact, shattering them and creating 2 distinct groups of debris. Most of the ejected material, about 70%, was flung southward at shallow angles and high speeds. That was the moment when success started to show its hidden cracks. The discovery of the accelerated boulders forced scientists to rethink everything. Tony Farnham, an astronomer at the University of Maryland and author of a key study on DART's debris, was blunt. We were able to deflect an asteroid, knock it out of its orbit. But our research shows that while the direct impact of the spacecraft caused that change, the rocks that were ejected gave it an extra push almost as big as the impact itself. That was the disturbing irony. DART's success didn't come only from the planned collision, but also from side effects no one had predicted. The debris carried 3 times more momentum than the spacecraft, generating forces in directions that were perpendicular to the original impact path. That meant Dimorphos's orbital plane might have been tilted by up to 1 degree, potentially making the asteroid tumble erratically through space. But there was more. Later analyses showed that the fragments weren't scattered randomly. They clumped into 2 distinct patterns, with a notable lack of material in other areas. As Farnham pointed out, we saw that the rocks were not randomly spread out in space. Instead, they were grouped into 2 very distinct clusters, with no material in other places, which means something unknown is at work here. That something unknown was a nightmare for planetary defense. If every asteroid responds in unpredictable ways to an impact, depending on its composition, density, internal structure, and surface topography, then every future mission would be a shot in the dark. Comparisons with the 2005 Deep Impact mission, which struck the comet Tempel 1, confirmed the differences. While Deep Impact produced a smooth, continuous ejecta plume, DART created chaotic, thread-like structures. The physics of planetary defense was turning out to be much more complex than any model had suggested. As the months went by and more data was analyzed, the scientific community had to face an uncomfortable truth. In April 2024, researchers confirmed that some of the larger DART boulders might be on a collision course with Mars, with an impact expected in roughly 6,000 years. Even though that sounds far off, the discovery raised deep ethical questions. Are we creating threats for future human colonies on other worlds? Even more unsettling was a simulation done in August of the previous year, suggesting that smaller fragments from the impact could hit Earth in about 30 years, possibly creating a spectacular meteor shower. Although scientists said those fragments posed no real threat, the mere possibility that our attempt at defense could create new risks was enough to set off alarm bells. The real point of tension came with the research of Rahil Makadia, a NASA fellow at the University of Illinois. Makadia introduced the concept of gravitational keyholes, small regions in space where a planet's gravity could change the orbit of a deflected asteroid, making it come back on a collision course with Earth at a later date. If a mission like DART pushed a real asteroid through one of those keyholes, the danger would only be postponed, not eliminated. Even if we intentionally push an asteroid away from Earth with a space mission, we need to make sure it doesn't drift into one of these keyholes afterward. Otherwise, we'll be facing the same impact threat again in the future, Makadia warned. Every point on an asteroid's surface has a different chance of sending it through a keyhole after deflection. The margin for error was smaller than anyone thought. A poorly calculated mission could turn salvation into doom. Faced with these revelations, scientists adjusted their strategies. Makadia's team developed detailed probability maps of asteroid surfaces, identifying the safest impact zones that would minimize the risk of passing through gravitational keyholes. These maps took into account the asteroid's shape, surface topography, rotation, and mass. Ideally, a reconnaissance mission would visit the asteroid before impact to collect high-resolution data. But if time was short, preliminary ground-based observations would have to be enough. The European Space Agency scheduled the Hera mission for December 2026, with arrival planned at the Didymos Dimorphos system to study DART's impact site in detail. Hera would map the crater, measure Dimorphos's exact mass, and analyze the long-term effects of the collision. That information would be crucial to refine deflection models. But other questions remained unanswered. How can we accurately predict the behavior of asteroids with different compositions? Rubble pile asteroids, low-density bodies made up of loosely bound fragments, react differently than solid rocky asteroids. And how do we deal with asteroids that are discovered too late? When there's no time for reconnaissance missions, NASA was also looking into alternative methods, like the enhanced gravity tractor, a slow push technique that would apply a small but constant force over many years. China announced plans to test its own kinetic impactor on the asteroid 2020 PN1 between 2025 and 2026. But few details were released. The race for planetary defense was becoming global, but the risks kept growing. The truth about DART remains ambiguous. Was it a brilliant success or a dark warning? The mission proved that humanity can change an asteroid's orbit. That victory is undeniable. But it also exposed dangerous gaps in our understanding. The unexpected debris, the unpredictable physics of impacts, the gravitational keyholes, all of it suggests that planetary defense is much more complex and risky than we imagined. Scientists like Jessica Sunshine summed it up perfectly. It's like a cosmic game of pool. If we don't consider all the variables, we might miss the pocket. Humanity now faces a moral dilemma. Should we keep developing asteroid deflection technologies knowing we might accidentally create new threats? Or should we accept the risk and keep improving our tools until they're truly reliable? The answer isn't clear. The only certainty is that the next test may involve a real asteroid, and there won't be a second chance. Decades from now, DART will be remembered as humanity's first uncertain step toward planetary defense. Future generations will look back and recognize both the courage and the arrogance of that moment. We did manage to move an asteroid, yes, but we also created wandering fragments that still drift through space. Silent reminders that interfering with the cosmos demands humility. Maybe DART's true legacy isn't the success we celebrated, but the questions it left behind. While the Rubin Observatory detects millions of new asteroids and the NEO Surveyor telescope maps hidden threats, one thing remains: Earth is still vulnerable. And now we know that our own solution can become part of the problem.